Well, hello everybody. Welcome to BlueMarbleScience. Guess who's back? Hello, Anthony. What do you have for us today?
Question from Charlie. Does Anthony really believe that the atmosphere has layers of different gases? If so, why are we not in CO2 as it is more dense than oxygen or nitrogen?
Well, CO2 is not a gas, is it? It's a mixture of gases. It's carbon and oxide mixed together. So it's not really a gas. It's like a compound of gases.
Excellent, Tony. Let's hear that one more time.
Well, CO2 is not a gas, is it? It's a mixture of gases. It's carbon and oxide mixed together. So it's not really a gas. It's like a compound of gases.
So CO2 is not really a gas. Tony, CO2 is a molecule composed of a carbon atom and two oxygen atoms. Carbon cannot even exist as a gas. Oh boy. Need I say more? Hey Gladys. I think this dumpster's already on fire. A few weeks ago, after being totally destroyed by George Natchik on Jose J.G. Gonzalez's show, Anthony decided to go on Ranty Flat Earth's channel and try and redeem himself. He did about a 25-minute presentation on his usual bollocks regarding gravity not being a force and Einstein contradicting Newton and on, the normal nonsense that comes from Anthony. Most of which doesn't even deserve a response. But the clip you heard earlier is from the after show where Anthony is trying to answer questions being placed in the chat. And some of that is well worth the listen. So let's see what else Anthony had up his sleeve that day.
Okie dokie, so I've just asked for more questions, so we'll see what happens. Right, so from Jimbo. Mass per unit volume and density. The difference, do you know it?
Mass per unit volume and density. Well, density is mass over volume. And what was the first bit?
Well, that was it. It was the full question is, Riley, mass per unit volume and density. The difference, do you know it?
Mass per unit volume. Yeah, that's mass.
No, numbnuts. Mass per unit volume is density. Is it that per thing that's giving you a problem?
And then density is mass over volume. So the difference is the volume.
Aha, I was right. It is that per thing that's a problem for you. Anthony, when we say something like mass per unit volume, that's the same thing as mass over volume. Mass divided by volume will give you mass per unit volume. Do you get that? I mean, come on. This is fourth grade stuff.
Okay, so how do you calculate the acceleration from falling if you have the density of the gas and solid object?
Oh, that's easy. Look up the definition. Well, okay, so the density is the density of the object divided by the density of the fluid based on water. So you get a ratio, and then from the ratio that you get from that, then you can calculate, or you can then apply the ratio and work out. Well, I don't know how it works because I'm not a mathematician, but if you just look up specific gravity.
Okay, so you know about as much about this as a pigeon would know about a claw hammer.
And then look up actual specific gravity without gravitational forces being applied, and you'll see that it's literally the density divided by the medium, and then that ratio, it tells you how far away from its equilibrium point it is, and that there's a correlation between its acceleration. Now, that's the mathematical answer. Whether it's true or not, maybe it's true, maybe it's not, I don't know, but the answer lies in the definition of specific gravity for the ratio that you get from it without gravity being applied.
Well, after all that word salad, let's say we try some Newtonian physics. I've got the mass of the Earth, the radius of the Earth, and the gravitational constant listed up there. Feel free to check these numbers. And Newton's equation, which tells us force is big G times the product of the masses divided by the square of the distance between their centers. So let's assume we have a second mass that's 100 kilograms. And let's plug all that stuff into Newton's equation. We end up with a force, attractive force, between the two masses, the Earth and the 100 kilogram mass, of 980.72 newtons. But that's a force, right? Kilogram meters per second squared. We're not looking for a force, we're looking for an acceleration. Fortunately, Mr. Newton gave us another equation that says F equals ma. In other words, acceleration is force divided by mass. So we simply take 980.72 newtons divided by 100 kilograms, and we get an acceleration of 9.8072 meters per second squared. Amazing. We actually measure 9.81 meters per second. Same thing. I wonder how that works out for us when we use the flat earth pseudoscience method. Let's take an object. You said it was the ratio of the density of the object to the fluid it's in. Okay. Let's take an imaginary object that has a density of 100 grams per cubic centimeter. And let's put it in an imaginary fluid that has a density of 0.1 grams per cubic centimeter. Use any numbers you like. Divide the object density by the fluid density. That would be 100 divided by 0.1. That's 1,000. But 1,000 watts. The units just disappeared. This is a dimensionless number. It's a constant. So now how in the hell am I going to get 9.8 meters per second from that? What do you think we ought to do? Maybe you ought to ask this guy. He looks like he's about as bright as you are.
Right, okay, so somewhat of a question from Rock Farmer. Question part one. Well, actually, I'll better wait for him to put his part two in because he's got an...
No, just ask part one.
Do I understand correctly that will the acceleration depend on the relative density between the object and the medium it is falling through?
The acceleration by definition is a force.
Acceleration by definition is a force? No, you idiot. Acceleration is a force divided by a mass. You say something stupid like that again, I'm going to give the claw hammer to the pigeon and let him drop it on you.
When an object is placed on a set of weights, what you're actually measuring is not the force of gravity on that object. You're measuring how far out of its disequilibrium it is. And what I mean by that is, if you get an adult and he weighs 15 stone and you stand him on a set of scales, he should weigh 15 stone when you put him in water as well. But we know that the medium change, the density variation, is changing this relative weight. That's why relative density is a thing. But what you're actually measuring is not gravity. And we know it's not gravity because if it was gravity and it was a force, even though Albert Einstein says it's not, the gravity that you're claiming that we're measuring is a 50 millionth of the object's weight, as per Henry Cavendish. There's no getting past that. So if you're 15 stone, gravity, according to Cavendish, is a 50 millionth of that 15 stone. That's it. So everything else is down to the mass relative to the medium it's in. And we can demonstrate that by putting it in water and showing that it doesn't measure the same value, because water is way more dense than air. So I've lost track of where I was at now with regards to the question.
Okay.
But
Well, Anthony, I imagine talking in circles like that made you dizzy. That's probably why you lost track of where you were. But once again, you said something in the middle of all of that that is just absolutely wrong. You have consistently misrepresented Cavendish, and you're doing it again. And we're going to call you out on it again. You said gravity is 1/50 millionth of the weight of an object, which is totally incorrect. We're going to go through it this time and show you exactly how wrong you are. You see the part I've highlighted there? This is the part that Anthony refers to. It says very plainly, as the force with which the balls are attracted by these weights is excessively minute, not more than 1/50 millionth of their weight, it is plain that a very minute disturbing force will be sufficient to destroy the success of the experiment. Now let me tell you just a little bit about Cavendish. He was trying to measure the density of the Earth, not the gravitational attraction of the Earth. He was trying to measure its density. He was doing that by measuring the attractive force between two masses. Here's a simple schematic of the experiment. Cavendish had two small masses, the little red balls there suspended on a beam from a torsion wire, and then he had two larger masses that he could rotate from one side to the other. And by measuring the period of oscillation of the beam with the small masses on it, he could determine the attractive force between those masses and the large mass. So let's try some Cavendish for dummies. Cavendish had large weights that weighed 158 kilograms and balls that weighed 0.73 kilograms. The two weights and the two balls ended up producing an attractive force of 2.9 times 10 to the minus 7th newtons. That's a very small force. On the other hand, the weight of the balls due to gravity is 14.32 newtons. The ratio of the weight of the balls to the attractive force between those balls and the 158 kilogram weights is 149 millionth, close enough to a 50 millionth. That's where the number comes from. So Anthony, it is really time for you to stop lying about this. I think we would all appreciate it if you would stop misrepresenting it. You know, there was a lot of stuff in this video that we could go over, but I think that's probably about enough for one sitting. Maybe we'll come back and revisit some of the other nitwittery that was happening. Hope you enjoyed watching it. If you did, please don't forget to like and subscribe. Just push those two little buttons down there under the red arrow. And we'll catch you guys on the next one. Hey, Gladys, we're out of here.